Conductor material. Introduction. The search for a good conductor of electricity began with the commercialization of power generation, transmission and distribution, and utilization. Good conductors were also required for the manufacture of associated power equipment. Copper had long been identified as the ideal conductor of electricity, not only for power transmission and distribution but also for connected power equipment such as generators, transformers, motors, and switchgear. The metal was so much associated with the industry that any resistive loss in a conductor was termed copper loss. International Annealed Copper Standard, IACS, established in 1914 had pegged the conductivity of pure copper as 100%, and the conductivity of all other metals and alloys is still expressed as a percentage of this standard conductivity. Interestingly, even today, many consumers are prepared to pay a premium to install copper conductors for certain applications because of its perceived higher reliability. With the increase in demand for power, it became imperative to search for an alternative material for the conductor to meet the demand and offer cost benefits. The volatility in the price of copper hastened the need to find a substitute. Aluminium, an element that is abundantly available on the planet, had also been identified as a good conductor of electricity. In time, driven by cost considerations, aluminium, with a conductivity of 55% to 62% of copper, was widely accepted as a replacement in overhead conductors, cables, switchgear panels, and busbar systems. The selection of conductor material is dependent upon application, ambient environment, and system parameters, among other project-specific requirements. Some of the properties that need to be considered before selecting the material are resistivity, conductivity, mechanical strength, fatigue strength, creep resistance, surface hardness, good dimensional stability, thermal conductivity, painting, coating, and plating, weldability, workability, low weight, low procurement cost. Resistance to corrosion. Corrosion can further be classified into oxidation, chemical corrosion, galvanic corrosion, crevice corrosion, pitting. Copper. Copper occurs in nature in a usable form and has been shaped and used for the past 10,000 years. One of the jewelry pieces made of copper, found in modern Iraq, dates back to 8000 BCE. The metal has been extracted from sulfide ore since 5000 BCE. Modern-day copper is extracted predominantly from a sulfide ore or an oxide ore. The process comprises mining, crushing, concentration, smelting, refining. After crushing, the concentration of ore is carried out by the froth flotation process. The concentrate is subjected to smelting to form matte. The matte is subsequently converted to blister copper. The purity of blister copper is increased by fire refining. It is further refined electrolytically to high purity copper. The refined copper is 99.99% pure and marketed in sheets of a thickness of 1 mm, 1/24 inch, and a size of a 1 meter square, 10 feet square. Most of the manufacturers of conductors use the wire bars, cathodes, or high-purity scrap as the input raw material. These are melted in a controlled atmosphere and extruded in stages to specified dimensions. The extruded bus bars are then heat-treated for the desired temper, hardness. Copper to be used for electrical purposes should be of high purity and good conductivity. It is important to note that the conductivity of copper is highly sensitive to the impurities. A very small percentage of specific impurity will drastically alter the resistivity and consequently, the conductivity of copper. Therefore, the conductivity of copper cannot have a direct correlation to its purity. Copper smelting. The concentrate is subjected to smelting to form copper matte. Copper refining process. Copper refining is an electrolytic process. Copper refining. Copper refining plant comprises series of cells operating on low voltage high direct current to execute the electrolysis process. In 1913, International Electrotechnical Commission defined International Annealed Copper Standard, IACS, to have 100% conductivity with specified properties at 20 degrees Celsius or 68 degrees Fahrenheit. They are volume conductivity, mass conductivity, density, temperature coefficient of resistance. High conductivity copper is classified as C101 or Cu, ETP, C102 or Cu, FRTP, C103 or Cu, of, C101 and C102 tough pitch HC copper. Tough pitch copper is produced by remelting or fire refining electrolytic cathodes manufactured by the primary metal extraction plant. A small amount of oxygen is introduced to scavenge the impurities. Oxygen manifests itself as uniformly dispersed cuprous oxide particles. The oxygen content is of the order of 0.02 to 0.05%. However, its presence can give rise to porosity if heated in a reducing atmosphere, as during welding. This phenomenon is called hydrogen embrittlement. Tungsten inert gas or metal inert gas welding, in a reduction-free atmosphere, ensure welding, free of porosity, and fissures. C103 Oxygen-free HC copper. Oxygen-free copper is produced by melting and casting under a controlled atmosphere, a pure form of raw material. It results in a purity of 99.95% copper, with a conductivity of a minimum 100% IACS. Aluminium. Aluminium is a highly reactive element and is found in nature as a compound. The metal was extracted on an industrial scale only in the late 19th century. Aluminium is the third most abundant element on Earth after oxygen and silicon. It has been alloyed and processed to meet the specific needs of a variety of industries. They are used as architectural sections in building industries or rolled in plates for shipbuilding industries. The present discussions will be limited to its application in the electrical industry as a current carrying conductor. The process of extracting aluminium comprises mining, concentration, extraction. Aluminium ore is called bauxite and it is mined as hydrated oxides of aluminium with silica, ferric oxide, and titanium dioxide as predominant impurities. The separation of alumina from the ore is achieved by grinding the ore with water and leaching the same with hot sodium hydroxide. The produce is then calcined to give pure alumina. The process used worldwide for the production of aluminium from alumina was discovered by Charles Martin Hall in the USA and Paul Hérault in France. Alumina has a very high melting point. It is therefore dissolved in molten cryolite and aluminium is extracted by an electrolytic process where graphite is the anode and the bath is the cathode. Aluminium extraction is a very energy-consuming process and requires approximately 2 tons of alumina and 17 megawatt-hours of energy to produce 1 ton of aluminium. Pure aluminium is expensive to manufacture and has very poor mechanical properties. Commercially viable high-purity aluminium, grade 1350, with temper H111 has a conductivity of 61% IACS. Most of the sheets required for the fabrication of conductor and enclosures for isolated phase bus are rolled from this grade. Sheets are manufactured by passing an ingot from the furnace through a series of rollers to reduce the thickness in stages to the desired value. The sheets can be hot rolled down to a thickness of 5 mm, 3/16 inch. Further reduction in thickness is carried out by cold rolling. Cold rolling marginally improves the mechanical properties of the sheet. Substitutable alloys for grade 1350 are 1050, 1100 and 1199. All have a purity of 99.50%. Controlled quantities of magnesium and silicon are added to form magnesium silicide alloy and subsequently heat-treated to enhance the mechanical properties of the busbar without excessively sacrificing the conductivity. Grade 6101 T6 was developed with a conductivity of 56%. Higher mechanical properties are obtained with heat treatment and cold working, extrusion. Aluminium alloys manufactured to grade 6061 T6 and 6063 are used as busbar material in outdoor switchyards. Hall and Hérault process. The Hall-Hérault process is the major industrial process for smelting aluminium. It involves dissolving aluminium oxide, alumina, obtained most often from bauxite, aluminium's chief ore, through the Bayer process, in molten cryolite and electrolyzing the molten salt bath, typically in a purpose-built cell. Potline in an aluminium extraction plant. The electrolysis is carried out at low voltage and very high direct current. The process is very energy intensive. Thank you. Mr. Balachandran graduated with a bachelor's degree, B.Tech, in electrical engineering from the Indian Institute of Technology, Madras, India, in 1967, and obtained a master's degree, M.E., in power engineering from the Indian Institute of Science, Bangalore, India, in 1970. He is a Fellow of the Institution of Engineers, FIE-India, Fellow of Institution of Engineering Technology and Chartered Engineer, FIET-UK, and Life Senior Member of the Institution of Electrical and Electronics Engineers, IEEE-US. He was the founder director of Power Gear Limited and Busbar Systems, India, Limited. He has worked in manufacturing industries in India and the UK and is currently an advisor. He has engineered several busbar systems that have been manufactured and installed in various countries, including isolated phase bus for the largest hydroelectric power plant, 26 by 800 megawatts, at the Three Gorges project in China. During his professional career, he has developed and tested a range of bus products and their accessories. His area of interest also includes switchgear, instrument transformers, and power system analysis. The book, An Introduction to Busbar Systems, authored by V. Balachandran, is case-bound, hardcover, size A4, 386 pages, printed on 100 GSM glossy paper. Copies of the book can be purchased with a requisition to Bala at busbarsystems.net. Black and white version of the book is for sale in India, Afghanistan, Bangladesh, Bhutan, Nepal, Pakistan, and Sri Lanka at a cost of 4,500 Indian rupees plus freight. Color version of the book is for sale in all other countries at a cost of US $126.00 plus freight.